Okay, I think we're good. Oh, why is that down there? I don't want that. There we go. All right, so Extrema. We're going to take a look at Extrema today. And this is, as I was saying, we're starting the most important part of our discussion of differential calculus. And then this culminates with the process of optimization, which is a really big, important part of calculus. And then once we're through with that, we're going to shift gears into the other type of calculus, which is integral calculus. And we'll get a good introduction into that for the remainder of the year. Okay, so Extrema. We're going to talk about Extrema, and relative to these Extrema, related to the Extrema, there are some important terms that kind of sound like the album titles from this hair metal band we're talking about. Extrema is their first album. It's relative Extrema. That's one of the topics we'll talk about today. That was their second album. And then Global Extrema, that's their world tour live album. And then Absolute Extrema is their greatest hits album. So we're going to touch on all this stuff today. Okay, so Extrema. What does it mean to be an extremum? The singular of Extrema is extremum. Extrema is plural. There are two different types of extrema. You can have minima and maxima. Singular would be minimum and maximum. And we've touched on this stuff. I know in Algebra 2 we talked about this stuff a little bit. So these are the extreme values of a function. We would say that f of c, so the function evaluated at c, is the minimum of our function f on some interval I, if every place on that interval, f of c is less than or equal to f of x. Okay? Whoops, hang on. I got to take this. Hang on. Hello? Hey, Derek. Okay, we're back. We're back. Sorry about that. So as long as for every value of x in our interval, if f of c is less than or equal to f of x, then that makes f of c a minimum, right? And that makes sense. In other words, it's the lowest point on the function on this interval I, okay? And what's interval I? Well, we could say, for example, it's the closed interval from a to b. So x is greater than or equal to a and less than or equal to b, okay? F of c is a maximum on this interval if for every value of x in this interval, f of c is greater than or equal to f of x. In other words, it is the highest point, or it's tied for the highest point, right? Then that makes it a maximum. Now, there are different types of maxima and minima that we could talk about. Okay, we could talk about if we're only referencing this value of the function, this point at c f of c, with regard to this one closed interval here, then we would say that it is an absolute minimum or an absolute maximum if on that one interval it is the highest or the lowest point. Okay, so in other words, let's think of our ant. We'll go back to our calculus ant again. We haven't referenced him in a while. So with our calculus ant, if our calculus ant was constrained to only crawl on our function along this closed interval, so he could walk left till he gets to the point where x equals a, or right until he gets to the point where x equals b, or anywhere in between, right? He would be at an absolute maximum if on that closed interval he was as high as he could possibly get on that interval. That's an absolute maximum. And an absolute minimum would mean he is at the absolute lowest place he could get on that interval. Okay. Now that's distinct from a relative minimum or a relative maximum, and we'll talk more about those in a moment. Those just mean relative to the places to the left and the right of where he's standing, he's at the highest point or the lowest point. Okay. So it doesn't necessarily have to be the highest or lowest point on the interval, but relative to the places in his immediate vicinity, in his immediate neighborhood, we'd say in math, he's at the highest or the lowest point. So that's going to give us a distinct shape, and we'll talk more about that. And then we say a global maximum or a global minimum means that on the entire domain of mathematical domain of this function, we call it the natural domain. So the biggest possible domain for that given function f of x, if the ant is at the highest place he could ever conceivably get, regardless of the interval we're talking about, then that's what we call the global maximum. If he's at the lowest point he could conceivably get to, regardless of any intervals we're defining, just on the entire function, then that's what we call a global minimum. Okay, give me a 1 to 5 on that real quick. Is that all making sense? Okay. Again, absolute maximum refers to highest or lowest point on an interval. Relative maximum or relative minimum refers to the lowest or highest point in his immediate vicinity. And then global minimum or global maximum means the highest possible maximum, lowest possible minimum the ant could ever get to on the entire function. Okay, so for example, for a parabola that's opening up, the vertex would be a global minimum, right? Because there's no way the ant could ever get any lower than that because the function could never go lower than that based on the shape of the function. Okay, so let's look at a couple quick examples here, just some pictures. So we're going to talk about absolute extrema for these examples here. So we're looking at this interval. This is a closed interval from -1 to 2, right? Because look, the endpoints are solid. Okay, so we've got to put the closed brackets at the edges of our interval. And does it make sense that this point right here at the right edge of our interval is the absolute maximum? Okay, on that interval, that's the highest that the ant could go. It's not the highest he could go on this function, right? The function goes up infinitely far, but we've constrained our interval right now to only be from -1 to +2 inclusive of the endpoints, right? So on that interval, that is his absolute maximum. He has an absolute minimum down here at the point 0, 1, right? It's the lowest he can go. Okay, all makes sense. Now, what about this guy right here, this picture? Okay, this is a different kind of interval, right? This is an open interval. We are not containing, it doesn't contain the x values -1 or +2. Does it make sense here that although there is a minimum, right, there is a point where the ant could stand and say, I am at the lowest point on this interval, there is no maximum, right? There's no maximum because there's no endpoint, right? We're not including that endpoint. So you might be thinking, well, okay, well, let's just pick the point next to that, right? The point next to the endpoint then inherits the maximum status. What's wrong with that thinking, though? What's wrong with that thinking? Why don't I just pick the point next to the endpoint, and when the ant is standing there, he's at the maximum? How come that doesn't work? Can anybody explain that? Be brave. Let me ask you this. Is there a point next to the endpoint? There's not, right? You can't define a point that is quote unquote next to that endpoint. Because if you think you've defined that point, all you have to do is zoom in a little bit and you'll find that there are an infinite number of points that you missed. Everybody get what I'm saying? This a good analogy. You remember that example I did back in Algebra 2? I referred to this quite a bit, where if I was standing facing my door of my room, and every second for the rest of eternity, I was going to cut my distance to the door in half. Do I ever get to the door? No, but do I ever stop moving? No, right? I can always take increasingly smaller steps and always move towards the door and yet never get there, right? And so if I had an infinitely fine Sharpie, you remember this example, and I put a mark someplace between the door and my foot, there is no point that I could ever draw that I wouldn't eventually step on, right? And so for that reason, there is no point next to the door, or in this case, next to that endpoint, right? And so we can't define a maximum. The ant could never stand at the highest point because all he'd have to do is take an eensy weensy little ant step further along, closer to the endpoint, and he'd be a little bit higher, right? Okay, so in other words, there is no absolute maximum in this case, but there is an absolute minimum. And then in this case right here, it's the opposite, right? Here, the ant could stand on that endpoint and be at an absolute maximum, but because we are excluding the vertex, he could never actually stand on a point that is the lowest. Okay? Give me 1 to 5 on that. Does that make sense? Okay? All right. So we're going to introduce an existence theorem. There's about, four or five something of these existence theorems that pop up a lot in calculus. The extreme value theorem, and by when I say existence theorem, this is an example of a theorem where if we meet the criteria, then it guarantees the existence of something, right? Remember, we had the intermediate value theorem earlier in the year, where if we met the criteria, the theorem guaranteed that there was going to be some intermediate value that the function went through. Vaguely remember that, right? Well, this is another one like that. If we meet the criteria, this guarantees the existence of something. So if f is continuous on a closed interval, that's our single criterion in this case. If f is continuous on a closed interval from a to b, then f has both an absolute minimum and an absolute maximum on that interval. Doesn't that make sense? Think about that logically, right? If I have to set my point down, because we're including the endpoints, I'm going to set my pen down on the graph at x equals a. Because the function is continuous, I can't pick it up off of the board until I move to the right to x equals b. It's impossible for me not to, at some point along that interval, define a highest and a lowest point. Everybody agree? Okay. All right. So, and I'll tell you what, I'm going to skip forward one real quick here. So let's just kind of prove that, right? So if I am going to put my pen down, this is going to look kind of goofy because I'm not at my board at school. So this is going to be a little bit awkward, but we'll do my best. So if I put my pen down someplace at x equals a and there's a solid endpoint, I can't pick my pen off the board until I get to x equals b over here. Well, that's not too terrible. Then look, it looks to me like that's pretty bad. There's my maximum somewhere, right? My absolute maximum. And my absolute minimum in this case is the right endpoint. It's impossible for me not to have a highest and a lowest point, right? There's no way I can avoid that if I have to draw it without picking my pen off the board, okay? All right, so relative extrema. Sometimes these are called local extrema. Remember from our discussion just at the beginning here today, these are the types of extrema that define a place where in the ant's immediate vicinity, he is at the highest or lowest point, right? Well, what's that going to look like? So if there's some open interval containing C on which f of C is a maximum, then f of C is called a relative maximum of f. If there is some open interval containing C on which f of C is a minimum, then f of C is called a relative minimum. Essentially, a relative maximum has to be a peak. In our two-dimensional universe here, on which we graph our functions, right, my board, then that just means we've gotten to a peak. The ant has walked to a peak of some kind of a mountain peak or the peak of a hill, right? A minimum is essentially a valley. Okay, that's all. These are topological features in our two-dimensional graph or two-dimensional space, right? A maximum looks like a peak, a minimum looks like a valley. What am I doing here? Okay. No, we don't. That's not important. So examples of relative extrema, right? So here's one function, f of x right here, that has a relative extremum, a maximum, at the point 3, 2, right? We can see that if an ant's walking along this topography, that's where he hits, it's kind of a gentle rolling peak, but it's a peak, right? That's the peak of a hill, okay? And it's got, notice, I want you to make a connection here too. Whenever we have this type of relative extremum, in this case, a relative maximum, notice that the tangent to the curve at that highest point is horizontal. You make that connection? Okay. If it weren't horizontal, he wouldn't be standing at the peak, would he? Right? He'd either be walking uphill or downhill if the tangent weren't horizontal. Okay, here's another example. If we have the function f of x equals the absolute value of x, well, that's giving us a valley, isn't it? Right? So that's an example of a relative minimum. Okay. Now this time, is there a tangent line at the vertex of that absolute value function? Thumbs up, yes. Thumbs down, no. Is there a tangent line there? Isaac is shaking his head no, and he's correct. Yeah, Lily gave me the thumbs down. She's correct. Right? Because a tangent line would mean that there's a derivative there, right? What does a tangent line do? The slope of a tangent to a curve is just telling us the slope of the curve. So that's the value of the derivative, right? Remember that we haven't talked about this in a little while, but the slope of a tangent to a curve is the job of the derivative function to tell us what that is, right? But the derivative is undefined at the vertex here. How come? What's our simple explanation for why that derivative is undefined there?
There's a sharp corner.
There's a sharp corner, right? There's a sharp corner, so no derivative exists there. And it doesn't fit the criteria of a tangent, right? With a tangent, remember what happens with a tangent. Let's look at this one right here for a second. If I zoom in further and further and further, and I flatten out the curvature by zooming in, the green curve would eventually look exactly like the purple tangent line, right? Everybody agree? If I just kept zooming in. But down here, that's never going to happen, right? No matter how far I zoom in on that vertex, it always looks the same. It always looks like a pointy vertex, doesn't it? We never remove the curvature, and so there can be no tangent line. So this is a valley, but this is the kind of place where we get a valley where we don't get a tangent line. We get an undefined derivative because it's a sharp corner. Okay? Let's look at another example. And we're going to connect all this stuff and try to look at some patterns here after we're done exploring this a little bit more. So here's an example where we've got two extrema, right? We've got a relative maximum and a relative minimum. And these are both the types where they have tangents to the curve. The derivatives exist at these peaks and valleys, right? So those are, we might call those smooth features. And this is a sharp feature, okay? All right, so let's see. We can make a generalization here then, right? We know that we get jagged peaks wherever a derivative is undefined. It would work for valleys also. And we get smooth peaks wherever we have a zero derivative, in other words, a horizontal tangent line. Same thing works with valleys, right? We're going to get a U-shaped valley, like a glacial valley, wherever we have a horizontal tangent line, and we get a V-shape, like a river carved valley, wherever we have an undefined derivative that's a minimum. Okay, very important. We're going to make those connections. Okay, so we can make an important, we can conclude something very important about this. Relative extrema, peaks and valleys, have to occur. Those we've seen every possible type of relative extremum. They're all peaks if they're maxima, and they're all valleys if they're minima. they're either rounded or sharp. Okay. So where would those things occur? Well, if we look back at these previous slides, it's not an accident that they always occurred at places where the derivative equaled 0, where we had a horizontal tangent, or the derivative was undefined, where we have a sharp corner and an undefined derivative, right? So if we want to go looking for our relative extrema, and that's something we're going to want to be able to do with these functions, one of our important jobs in calculus is we want to be able to locate all of the relative extrema. When we apply calculus to science or economics or any kind of an interesting application, some of the places that we're always very interested to find are the maxima and the minima, right? So we know that those always occur at places that we call critical numbers of our function, okay? So there are two types of critical numbers. One type of critical number are the values of x, or whatever our input is, where the derivative is equal to 0. So if f prime of c is equal to 0, then that means that c is a value of our input that we're going to call a critical number, okay? The other place, of course, would be, and then there are some examples, right? There's some examples of those types of critical numbers, right? The other possibility would be if the derivative is undefined at that value. So c is a critical number if f prime is undefined at c. F prime of c is undefined, okay? And of course, that we've seen examples of that also, right? That would be a sharp peak or a sharp valley, okay? But you got to be careful with this because not all critical numbers yield extrema. Just because we found a critical number doesn't mean that it necessarily is going to give us a peak or a valley. Here's an example of a critical number, right? Here's a place on this function, and that's not a very good, that curve, it's supposed to be horizontal in the middle. You get the idea, right? You could have a function that has a horizontal tangent, but it is not, in fact, a minimum or a maximum. This is what we're going to come to call an inflection point, okay? You could have a place in a function where the derivative is undefined because we have a vertical tangent line, but that's not necessarily a minimum or a maximum also, right? So you have to remember that when you're looking for extrema, they always have to occur at critical numbers, but some critical numbers could be false alarms, right? So we're going to have to always check our critical numbers to, in fact, see if they really do produce extrema. Okay, some will, some won't. Right? Here's an example of an actual function that has a horizontal tangent line at the point 1, 1, but that's an inflection point, right? That's not an extremum. Here's an example of a function that has a vertical tangent line at the point 1, 1, but it also, you can see, it's not an extremum. Okay. All right, so one more little theorem I'm going to throw out. Oh, hang on one sec. Be right back. Hold tight. Sorry about that. Hey, do you guys remember what time we get out of here?
11:40.
Thank you. Okay. Oh, God. Chuck, no bark. Come on, come here. All right, here we go. One more little theorem here. It's Fermat's theorem. So if f has a relative extremum at c, and if f is differentiable at c, then what must be true? You guys fill in the blank there. Think deductively here. Think logically. If it has a relative extremum at c, and if f is differentiable at c, what does that mean? And what does differentiable mean, by the way? To differentiate is a derivative, right? To differentiate means to take the derivative. So differentiable must mean, That kind of just means a little bigger. Sort of take the derivative of bull, right? We're able to take a derivative there. So if the function is differentiable at C and it has a relative extremum, what kind of relative extremum must that be? Differentiable means the derivative exists there, right? We can take the derivative. What do you think? Caleb, what's that mean? If f has a relative extremum, so it's got a peak or a valley at C, and the function is differentiable at C, what kind of a peak or valley must that be, Caleb?
Then it's not a sharp point, it's a curve.
Yeah, it's got to be a curve. So what's that tell you then about the value of the derivative there? What's it have to equal at C?
0.
It's got to be 0, right? Because it's got to be a horizontal tangent line. So the slope must be 0 there. Okay? All right. So summary. Relative extrema, peaks and valleys, absolute extrema are the maximum value or values and or minimum value or values on a specific interval. Global extrema are the maximum or minimum values possible on the entire natural domain of the function. Okay? All right. Okay. I gotta remember what the heck I was doing here. Give me a second. What was this one about? Okay, so I know one thing I'm going to ask you about this. So let's look at this first picture over here, right? This guy right here. Okay, does the extreme value theorem, and let's take a quick look at that. It's way back here. There it is. There's my extreme value theorem, right? In fact, I'm going to take a picture of that. And let's put that on this page. How about? Oh, come on. There we go. Okay. This will be good for your notes. So there's the extreme value theorem. Okay, in Exhibit A over here on the left, the door on the left, does the extreme value theorem guarantee the existence of an extremum on that interval? Yes or no? Thumbs up for yes, thumbs down for no. Seeing lots of thumbs up. That's right. Okay. It's a closed interval and it's continuous, right? I can draw it without picking my pen off the board. So it does guarantee the existence, and it's telling us that there's a minimum there, right? Okay. Now, let's skip over here to this far right example. Does that one work? Thumbs down, right? It doesn't work, right? Because I have to pick my pen off the board right there. What about the middle one? Does it guarantee the existence of a minimum? Okay, I'm seeing a little bit of both here. This is good. We got some debate going on. David, why not?
Because wouldn't technically you have to take your, I don't know, you take your pen off the board for the two endpoints?
Okay, because the endpoints, as we've currently got it drawn, I have to pick my pen off. That is a correct statement. Johan, you're also correct, though. You could be correct by putting your thumb up. How come? We can guarantee the existence of a minimum there. What do we have to do?
Well, I don't know. I just see a minimum there, so that's fine.
Okay, there is a minimum, so we ought to be able to guarantee the existence, right? What if we don't use those exact endpoints, though, right? What if we just define some slightly smaller interval where it is a place where the function is defined, unlike the current endpoints? Wouldn't you agree that I could define an interval that includes the value x equals 0 that is continuous? Everybody agree? So it works, right? I can just redefine. You were right, David, but I could just cheat. I could just define a slightly smaller interval where I could guarantee the existence of a minimum. Everybody see that? That's allowed, right? That's allowed to do. All this says is that we can define some closed interval, right? Where the function is continuous, and we can do that. Okay. Okay. Here's a good question that comes up, and if you were in the classroom, somebody would have probably raised their hand and asked me this at some point. Maybe not yet, but at some point this would have come up. I guarantee it. So does this left and right endpoint? Let's say that this is our function. It's only defined on this closed interval. Do we count the endpoints as relative extrema? Yes or no? Do we count them as relative extrema? Okay, the best answer is it depends. It depends on what we define the rules to be. And I like to bring this up because this is an example of a topic in math that is really not resolved. I mean, you could go to different classrooms and different teachers are going to tell you different things. Different textbooks tell you different things. I tend to think that it's most useful to think that, yes, you can define the endpoints as relative extrema. It makes more sense in many ways that you could do that. Okay, and here's my reasoning for that. My reasoning is that, remember how we defined when we were first talking about continuity on a closed interval? Well, we had to amend our discussion about what it means to be continuous at a point, right? Earlier, we had said that point continuity relies on an ant being able to approach from both directions and anticipate stepping on the same point from the left or the right. But at the endpoints, we couldn't do that, right? So we had to define these one-sided limits where we're approaching from the left or approaching from the right. And so because we have a vehicle like that for approaching a point from one side or the other, it just stands to reason that these really should be considered relative extrema, right? Because the ant, in my opinion, the ant can't approach from the left, this left endpoint. And so it would count as a relative extremum. It's like if he got to the edge of his universe and it just fell away, well, he's still standing on a point there that is higher than all of the points he has access to in his immediate vicinity, right? Okay, despite that, most high school and undergraduate textbooks say no. They say no, that it's not a relative extremum. And the rationale for that is that you can't approach it from both sides. Okay, so for now, we're going to go ahead and go with what the book says. Okay, but this really is an open discussion. And I tend to disagree with that, but you could talk to somebody else and they might tell you something different. All right, so I think we can skip through that. Well, you just tell me real quick. Does that one have an absolute minimum, an absolute maximum, or neither? And if so, where does it exist? Kirsten, you tell me what kind of absolute extrema does this one have?
A minimum.
Only an absolute minimum. You're correct, and that occurs at C2, right? Okay. How about this one right here? Structure. What do you think? Emma, what do you think?
So I was really confused. I don't know, none. I don't know.
Well, now just think about it in terms of the graph. Is there a place where the ant could stand and be at the lowest point on the interval, the closed interval from A to B?
Yeah, and B.
There, at A, right?
I mean A.
Yeah, right. So there is an absolute minimum, right? There is a place you could stand and be at the lowest point. What's bugging you is that there's a break in the function, right? It's not continuous from A to B. That's all right though. It is continuous from A to some point to the left of D, isn't it? Right? And so there is a minimum there. There is a minimum on this other section too, but this is a lower minimum than that minimum is, right? Here's another way to think about this. The extreme value theorem guarantees the existence of a minimum or maximum if you meet the criterion. If the function is continuous on the closed interval, then it guarantees the existence of an absolute minimum and an absolute maximum. Is the converse necessarily untrue, though? If we don't meet the criteria, can we guarantee that there are no absolute minima and maxima? No, right? There still could be. Right? This one doesn't go both ways. Okay? Right? This is not a biconditional statement. This is only a conditional statement. It only flows from left to right. Okay, so there is an absolute minimum at A. Is there an absolute maximum, Emma?
I'm sorry, what?
Is there an absolute maximum? There is a minimum, absolute minimum right there.
Could you go like one less than the undefined part or no?
Well, remember, we can't do that though, because if you think you're at the point next to it, there's an infinite number of points between you and the whole, right?
Mm-hmm.
See what I'm saying? So there is no absolute maximum, okay? But there is an absolute minimum. There is a place you can stand on this interval and be at the lowest point. How about this one? What do you think? Andrew, is there an absolute minimum?
No.
No. Is there an absolute maximum?
No.
How come?
Well, because that's a sharp corner.
That's all right, though. Sharp corners can be maxima.
So I guess it is. Then.
Yeah. Right. Remember, the only thing that's I think what you're confusing here is that a sharp corner is where the derivative doesn't exist, but the function does. F of C is equal to 1, 2, 3, 4, 5, right? The ant can stand at the point x equals c, y equals 5. And, he can plant his flag at the top of that peak and say that he was at the highest point in his universe, right? Okay? How about this one? What do you think, Johan? Is there an absolute minimum?
No.
No, there's not, because he can get closer and closer and closer to that endpoint, but never gets there, right? He can't step there. Is there an absolute maximum?
No.
Nope, because he can't ever stand on that point. He can get arbitrarily close to that point, meaning as close as he chooses to get, but he can't ever get there. Okay? Okay, so identify the graph here that has a local minimum value where f prime of A equals 0, A, B, C, or D. So give me a 1, 2, 3, or 4 with your fingers on this one. We want it, once again, we're looking for the place where it has a local minimum where f prime of A is equal to 0. It has a local minimum where f prime of A is equal to 0. What does that mean for us? F prime of A equals 0. What's happening at A? When are we out of here again, by the way? 40, okay. So what do we immediately think of? This is calculus speak for something, for what? F prime of A equals 0 means what? I think you just said it, David. What'd you say?
It's curved.
It's curved. Yeah, it has a horizontal tangent, right? The slope of the curve, meaning the slope of the tangent is 0. So where is there a minimum? This is just saying where is there a local minimum where we have a horizontal tangent? That would be a curved minimum. Which one has a curved minimum? I think I cut off part of there's more than one, isn't there? I think I was supposed to say which one has a curved minimum at D. At D. It would only be that one right there, for example, wouldn't it? Right? Okay, be 2. 2 of these have curved minimums at B, but only one of them has a curved minimum at D. Okay? Okay, what about this one? Now we want a local minimum value at x equals B where f prime of B is undefined. Did it say that on that last one? I just missed it. Oh, f prime of A is equal to 0. Sorry. F prime of A is equal to 0. So that would have been B, would have been right there, wouldn't it? Right? Okay. I just didn't read it. Okay, now what about this one? It's got a local minimum at x equals B where f prime of B is undefined. So what's that telling us right there? If f prime of B is undefined, what's that telling us? David, what's that telling us?
It's a point.
It's a point. Good. It's going to be a sharp peak or a sharp valley. In this case, it's going to be a sharp valley because it's a minimum. So where do we get a sharp valley at B? Right there. That'd be A, wouldn't it? Okay. Identify all of the points on the interval, closed interval from A to B, at which local and absolute extreme values occur. Okay, and I think we're out of time. Is it 40s when we're out of here? Okay, so this was kind of just today was an introduction to the vocabulary. We're sort of looking at conceptually, qualitatively, what does all this stuff mean? Where we'll move next time we meet, we'll kind of continue this discussion and we'll actually start to use calculus to find some of these places. So we'll actually do some problems. Does that make sense? Okay, have a great day. See you guys later. Bye.